Okay, super. Very good. So it's a pleasure to finish this exciting meeting with Tadashi Takayanagi from Kyoto University, who's going to tell us about entanglement of purification and holography. So Tadashi, please take it away.
First of all, I'd like to thank organizers for kind invitation to this really exciting workshop. And today I'd like to talk about our recent works related to the quantity called entanglement of purification and its holographic dual. And this talk is based on these three papers. And the collaborators are Arpan Bhattacharya and Pavel Kapta, who are postdoc in our institute, and Alex Yan, who is sitting there from Free University Berlin, and Masamichi Miyaji and Koji Umemo there, our graduate student. So let me begin with the introduction. So ADS-CFT provides a sort of geometrization of dynamics of conformal field series, as we also heard in many talks of this conference. And the one important manifestation of this feature is the correspondence between quantum entanglement, dynamics of quantum entanglement in conformal field theory, and dynamics of bulk geometry, namely gravitational dynamics. And one way to see this is to look at this quantity, so-called entanglement entropy, which measures the amount of quantum entanglement for pure states. And we can represent this entanglement entropy as area of minimal areas, area of minimal surfaces. So like this picture. And so we have some, if we have some gravitational waves, this area changes a little bit, maybe oscillates. And this oscillation corresponds to the entanglement oscillation. So it's dynamics between entanglement and the gravitational dynamics. They are correlated. And so good point of ADS-CFT, one interesting point of ADS-CFT is the correspondence between algebraic relations in quantum information is related to geometrical properties in gravity. And so one example is an inequality called strong subadditivity, which is a very fundamental inequality known in quantum information theory. So this is an inequality. So we have a SAB, the entanglement entropy for subsystem AB, A union B, and this is BC. This is always greater than this combination. But in geometrical side, holographic side, we can have a very simple geometrical picture. So if we compute entropy ABC, then SAB is related to this red surface, area of red surface, and this is this guy. BC is related to this blue surface. And we have this combination. We can think about just divide this way. So this surface covers ABC, but this is obviously artificial, and there's some even cusp singularity here. So there are smooth surface which really minimize area. So this clearly explains this inequality. So we can go further. That's so-called monogamy of mutual information. This is not always true for any quantum system, but only true for this holographic system, because the holographic system is so ADS-CFT predicts if we think about a strongly coupled and large n, large degree of freedom CF conformal field theory, it is really related to Einstein gravity, which we are assuming here, some classical geometry. So this is a result by Hayden, Hedrick, and Maloney, the famous inequality. So we can easily, from this kind of similar argument, we can show this inequality. So this is a mutual information. Mutual information between A and B is described by this. This is kind of monogamy inequality. But this actually characterizes a very special nature of holographic quantum state. And so go to the tensor network, which is the main topic of this workshop. So this is a key idea to understand some emergent spacetime which comes from quantum entanglement. So first proposed by Swingle, but there are many improvements, many discussions until now. And as far as I understand, it's not completely converged. It's like still ongoing. So it's quite an exciting subject. But anyway, so originally, if you take some quantum state in interacting theory, it is really algebraically complicated. So this is very complicated, but if you view this from the viewpoint of tensor network, we have a nice geometry, which namely, it's like some hyperbolic space. So like this is my mirror or mirror network or maybe happy code, and there are many interesting tensor network, but always looks like nice geometric picture. So there, entanglement entropy, we can, for example, compute this as a minimum cross-section, minimum number of minimum intersection between links and some surface which covers region A. as we saw in several talks in this workshop. So, and in this talk, I'd like to present some new conjecture which generalizes this holographic entanglement entropy, which I just mentioned. And also, this has a very highly motivated by tensor network argument. So these are contents of my talks. I just finished the introduction. I go to idea of so-called entanglement wedges, and this allows us to define some holographic counterpart of entanglement quantity called entanglement purification. Entanglement of purification is some generalization of entanglement entropy to mixed state and good correlation measure. And finally, give some heuristic derivation of this conjecture. So let me start with the entanglement wedges. So this is related to basic question in ADS safety, that which bulk region in some is dual to some particular region in conformal field series. So ADS CFT means CFT conformal field series is dual to some gravity in anti-Doshita space. So which region corresponds to which region? So very basic question. And so this is answer is the so-called entanglement wedge. So if we think about this is a bulk ADS, this is ADS, this is a boundary. Let's assume we take some time slice, and this is a region A. So this region A in the CFT corresponds to some region in the bulk, but the answer is simply given by this region called MA, which is an entanglement wedge, which is a region surrounded by this A and the minimal area surface. And so more precisely, this means that reduced density matrix in CFT low A is correspond to the reduced density matrix in the bulk, which is localized on this region, MA. So this is a very simple correspondence, and owing to many authors' efforts, we find this kind of correspondence. So we're going to use this. So then, but we can think about a little more complicated situation that subsystem is consists of two disconnected regions, region A and region B, like this. They are disconnected. In that case, we have two possibilities, basically. So we can think about the minimal surface, which covers A, B. Separately, also, we can think about minimal surface, which covers both A, B, like this way. So they compete. So we always should take a minimum among these two possibilities. So if they AB are far apart and AB is not so big, then actually disconnected contribution has a lower area. So this is preferred. So this entanglement wedge is now separated and disconnected. But if AB are very close to each other or are very large, comparably, that case this connected surface has a smaller area. So entanglement wedge is connected. So, so obviously, the second case is more interesting. And the first case is trivial in that sense. It's mutual information. If you compute this way, in holographic way, it's just zero. So no correlation at leading order of large N expansion. Though there are small correlation next order. But in this talk, I'd like to more interested in this second case, which are non-trivial entanglement wedge, which is a non-zero mutual information. So we expect a very strong correlation between AB. And in that case, so we would like to consider some very simple geometrical objects, which I think everyone can come up with if we look at this picture. So how much they are connected is characterized by minimum cross-section, which divide region A and region B. So this is a cross-section, so minimal area, a minimal cross-section in this entanglement wedge, which looks like wormhole, like some slot, and which separate AB. And so this is a minimal surface which divides AB, MAB in A side and B side. And next thing to do is one good quantity in this kind of context is always entropy. And to find entropy, we should always need to compute area. So motivated by that, we'd like to define some interesting quantity which we call entanglement wedge cross-section. And always we divide by 4 G Newton, follow from, Wittgenstein-Hawking-Homeland black hole and also holographic entanglement entropy. So, and we know these two guys are same dimension. So this EW defines dimensionless quantity, which much like entropy. But of course, we don't know at this point what kind of entropy this means. But anyway, this is a heuristic picture of this. So we are interested in this quantity, and then so our conjecture is listed here. And so this is a simple, this EW, this entanglement cross-section is equal to some information theoretical quantity, namely entanglement of purification. So that's I'm going to explain the definition of this quantity. But anyway, so if we can reduce this to a very simple case, like if total system, so we are interested in this AB is, as you can see, it's like a mixed state, right? So we trace out this other part, white part. So in general, rho AB is a mixed state, and this is a kind of interesting measure of mixed correlation between AB in a mixed state. But if we assume rho AB is a pure state, then this quantity is known to just reduce to von Neumann entropy. So this is just standard entanglement entropy. And left-hand side also just reduced to the holographic entanglement entropy, because it's just a minimum area surface. So that way, this gives some simple generalization of holographic entanglement entropy. And so first I'd like to explain what's the definition of the EOP, entanglement of purification. I just write it EOP. So this purification plays a very important role. So we can think this is very simply motivated, because entanglement entropy is a good measure of quantum entanglement for pure states. But unfortunately, this is not true for mixed states. There are many interesting measures, no? But one simple idea is to just anyway purify the system. Once we purify the system, so we can measure the amount of quantum entanglement by entanglement entropy. So this is what we do, but the problem is this purification. So purification means we have some mixed state rho AB, but we extend the Hilbert space. This is the extra part. A tilde and B tilde is extra part. And we put some additional Hilbert space, and we get the pure state. This is a purification. And then what we compute is the entanglement entropy for this A plus this extra part, A tilde. So this decomposition into A tilde, B tilde is somehow arbitrary. But once we fix this decomposition, so we can compute SA tilde for this pure state. But of course, this has huge ambiguity. So this result depends on how we purify the system, and also choice of A tilde and B tilde. So we have to do some optimization. We take a minimization of all purifications. So this is always should be true, but there are many candidates of psi, and we take a minimization. So anyway, this gives a single answer to this. And this quantity is known to be entanglement of purification. And this is always non-negative, and if this is 0, it's just a direct product. It's no correlation. And there are a bunch of interesting properties known for EOP, like this. And so this is just if we assume, so this is always bounded by SA. And if pure state just reduced to von Neumann entropy, and always bounded from below by half of mutual information. This is equal to each other for pure state. And this is also another bound, and this is the whole polygamy inequality. So this means that this is not a good quantum entanglement measure, unfortunately. But anyway, so this is an important inequality, and this is extensivity. If we get a larger system, so this correlation also gets larger. But so before I go to the holographic counterpart, I'd like to also give some numerical result, which we find in lattice setup of free scalar, mainly owing to the Alex Yann's contribution. And so this is to find some intuitive understanding of the behavior of entanglement of purification. So we computed the whole this free scalar and also Ising spins. And we can discretize a system like this, and we can choose A and B, some small size of subsystem. And we are interested in the dependence of EOP against separation, distance between these two regions, A, B. And we find this kind of plot. This is a plot, so the whole different value of actually this subsystem size. But anyway, so you see, so we notice some interesting plateau. Right? This is a very peculiar to entanglement of purification. On the other hand, if we plot similar thing for mutual information, it's just monotonically decreasing. So this means that there are some special effect for special distance. Just one side is separated. There are some enhancement, and at least we find phenomenologically we find this enhancement comes from the following observation that so somehow entanglement purification magnifies the contribution from classical contribution. So we have always quantum entanglement contribution plus some classical correlation. And classical correlation is very enhanced in this quantity called entanglement of purification. So we can see this in many examples and some schematic interpretation. So that way, it's somehow entanglement purification behaves slightly differently than mutual information. So this also motivates us to study this holographic counterpart of this quantity. So now we go to holographic entanglement purification. So already I explained, so we have a conjecture between these two quantities. And so we can confirm this inequality, which I just explained before. So it should be bounded by SA, but this is obvious. This is SA is just this divergent geodesic, but we are looking at this much smaller surface area. And if pure state, this white region is just disappear, so we have this area here. We have also easily derived this lower bound of half of mutual information because of this kind of geometrical analysis, very similar to proof of strong subadditivity. So this gamma A, this region gamma A area is bounded by this combination always, and V also bounded by this sum. This is just triangle inequality in geometry, and just sum of this. We take a sum of this, it just gives this inequality. And the polygamy inequality also something similar. This red guy is obviously smaller than this green guy and this black guy, sum of these two guys. And that way, everything just like a triangle inequality. It's very elementary. And we can also easily see also this extensivity. This actually comes from geometrical property called the entanglement wedge nesting property, which means that if we increase the subsystem, the entanglement wedge region also increases. This is also there a nice proof of this. And we can use this fact that just easily see EOP also increases. And finally, there's some as a bonus, we get some inequality which is not always true for quantum information theory in generic quantum system, but this is again somehow only true for holographic states. This is namely strong superadditivity. It's given by this inequality. So this is some counterpart of this monogamy of mutual information for entanglement entropy case. But so I'd like to also mention some. We have to be careful that so we claim that this minimum entanglement wedge cross section is equal to entanglement purification. And entanglement purification, we need a minimum. We take a minimization over some class of purification, not originally defined as just any purification. So we have to take a minimum of this entropy for any purification. But maybe for holographic theory, maybe we just take there are possibilities that we just take over all holographic state. Maybe. So there are smaller substate, we take a minimization of a smaller subsystem, subclass of the state, or maybe just all state, as is true for in original state. We have to be very careful. So, and this also motivates us to do some explicit calculation between CFT side and gravity side. Gravity side is very easy, just a compute area. But CFT side is highly non-trivial because this involves some minimization. But also because of that, it's good to compute this in CFT. So this is my coming talks here. And so first we look at tensor network. Let's look at some state described by tensor network. And we assume some usual correspondence between tensor network and ADS safety. This is highly conjectural, but let's assume ADS space, some time slice of ADS space is given by some tensor network. It's much like original conjecture by swing. And we have in mind something like happy model, which is a perfect tensor, which has a nice isometric property. So we start with this some tensor network. It corresponds to time slice of ADS. So there are many interesting developments, as already mentioned. So one basic principle is which we summarize as a surface state duality. So if we think about this tensor network, you can cut out some region as we like, and by contracting these tensors, we can define pure state. Some for each surface, we can call it a sigma. So sigma is some convex surface to avoid some subtle issue. So for each convex surface, we can associate one pure state. So this should be true for this tensor network description. So then, the computation of entanglement purification can be done. We can do as follows. So we have this is a boundary of ADS. It's just where we realize quantum states. So, and we talk about the region A here and region B. This is spins. Let's assume some spins, and this is the region A and region B. And this is the extra part is called C. So this is, and if we trace out C, we get low AB, like this. But we want to do some optimization, minimization against purifications. So of course, this gives one example of purification, but we can take a much smaller purification. So that means we do some compression of information. That means we can start with this region C, but we can go inside. Because this is isometry, so this does not change the reduced density matrix. But we have to stop at some point. This is memory. This is a point where we have minimal surface. If gamma AB, this surface is take a minimum value. If we go a little more, then it's no longer, satisfy this property that reduced density matrix is low AB. It changes. So that way, and so we end up at this point, this minimal surface, and next we have to choose what is A tilde and B tilde, right? So we can choose, but this is essentially the same as minimizing entanglement over this choice. And the entanglement is described by this number of intersection between this curve, sigma AB, and these links. So we minimize this link number. So that way, this is exactly the same procedure which we have in holographic counterpart. So this naturally explains why we find this entanglement, relation between entanglement purification and minimum cross-section in a very simple way in a tensor network calculations. And then, so we'd like to go another derivation. So this is based on the idea called path integral optimization. Already we had an interesting talk this morning about path integral optimization. And so let me quickly repeat the same analysis. That we start with two-dimensional conformal field theory on a flat space. Let's start with just path integral on a flat space, and that creates ground state of conformal field theory. But path integral optimization, we can say this is just equivalent to some special Weyl transformation, which preserve the same quantum wave function. So we should always end up with the same ground state of the conformal field theory. We're always interested in, let's assume, just a ground state of conformal field theory, and we want to get the same wave functional, but we just change the process of path integration. So we want to, if we discretize path integral into lattices, we want to reduce the computational cost. So namely, so this is something we define, so computational cost as a path integral complexity. That I will come back just next slide. But anyway, so we minimize this complexity, but still keep the same state. So this is a path integral optimization. And so this is special Weyl transformation. Weyl transformation is written this way. And we have to fix some boundary condition to guarantee that we get the same quantum state. So we change this phi, and we roughly coarse-grain anywhere we can do. So because of the theory is conformal invariant, we are allowed to do this. And we choose the most efficient coarse-graining. And so the path integral complexity is just defined by normalization of wave functional. We know that normalization of wave functional is not important, it's not physical, in the sense that state does not depend on normalization. But this normalization appears if you repeat many times of the numerical calculation path integral, you get a more factor, even though result doesn't change. We want to minimize this kind of extra cost. So this motivates us to call this normalization of wave functional as a complexity. And we know that in 2D CFT, there is a very nice story that this normalization is known to be equal to exponential of Liouville action. This is a very simple form of action, which appears in many places. And we can integrate. This is quite an integrable system. It has a lot of many good properties. And anyway, so we have this Liouville action. We take a minimum. So we solve equation motion. That's very easy. With this boundary condition, then we end up with hyperbolic space, which is really same as time slice of anti-De Sitter space. So this is a nice correspondence, and we can generalize this to more complicated case with excited state. We can insert some primary operator, and still we can do the same procedure. Then we end up with, for example, like black hole geometry, and that is exactly what we predict from ADS CFT correspondence. So if we put some operators, then that back reacts geometry and changes into what we expect from ADS CFT. So here's a sketch. And so it originally started with discretization path integral, quite fine-graining path integral. But we eliminate, for example, this part is just coarse-grained because this is a highly Euclidean path integral for a long time. So we don't care about the initial condition because it's damped completely. We have exponential beta h, and its beta goes to infinity. So initial condition is not sensitive to the final result. So anyway, so gradually fine graining. And this looks very similar to tensor network, mirror-like tensor network, but we have to be careful. This is a Euclidean. We are assuming it's a Euclidean gate here. But anyway, as we saw this, we end up with some hyperbolic geometry. And so using this idea, so I would like to think about this entanglement of purification calculation of that. And so first of things, we optimize the density matrix. To compute entanglement purification, we want to preserve the same reduced density matrix, but we need to minimize this entropy when we purify the system. So we use this idea to minimize this entropy. So we start with some reduced density matrix, and this is a standard picture of path integral. So this region AB is here, AB is here. And this is a cut. This is a Bragg state and a Ket state in the Euclidean path integral formulation, and we have a slit here. And so the thing is that this defines quantum state rho AB here, and we trace out the other part. So we are interested in 2D CFT and infinitely long system. Total system is infinite line. And we trace out this dotted part. And this AB is important, so we keep this only information of this rho AB. And we can choose some subsystem B tilde and A tilde initially, like this way. So, but this is just original purification, and this doesn't give good value. This is a very large. It gives a very large entanglement of purification. So we need to optimize. So for optimization, we use again this Weil transformation. So Weil transformation doesn't change this reduced density matrix, but we can squeeze the metric that minimize somehow entropy. So, but to make everything simple, so we just use this is a technical point, but we perform some conformal map into this setup. This is now A and B is here. This boundary is mapped to this one boundary here. But this is just technical point. And then this is some details, but anyway, so we optimize this metric by solving Liouville equation. That gives some minimum complexity, and we hope that gives some minimum entropy. And this is a solution. This is a solution. But still, we have one parameter, which is like this separation. This is position of Q. So separation between A tilde and B tilde is also parameter. We have to minimize over this separation. So we do this. So this is a parameter Q, actually. So we take a minimum of this result. And then what we get is this expression. P is so this AB is this two endpoints, AB, and P is just separation into AB. This is initial value. So this is initial input. APB is the initial input. And then, so we get this result. Epsilon is a cutoff, UV cutoff, and everything just completely uniquely fixed. And so we can now, it is interesting to compare this with gravity dual. So this in gravity dual, we have this picture. This is the AB, and this is the entanglement wedge, which I mentioned. So entanglement wedge is just half disk. And we can choose there a degree of freedom of choose this A tilde and B tilde here, but we can take just minimum, right, minimum length. This turns out to be the sigma, which is another circle, part of another circle, dual circle. And we can compute this way. So this holographic result precisely agree with this result for which we find for path integral optimization. So that way, so we find some derivation, this one derivation of this holographic quantity from completely CFT calculations. So we can generalize this calculation also of some more complicated cases. It works so far. Okay, so these are basically what I wanted to talk. And so this here is the conclusions. So this, my message is just gravity dual of entanglement purification is conjectured to be minimum cross-section of entanglement wedge. And we check this conjecture against two different computations. So one is a tensor network. This is a very heuristic approach. And another one is that this path integral optimization complexity, minimizing path integral complexity. And there are several future problems. So we want to understand which class we really minimize this entanglement entropy to compute this EOP, especially in the context of holography. So we find some interesting hint, right, of this path integral minimization may be enough to find this, but we need a more future work to have a conclusive answer to this question. And so it is also interesting to just directly derive holographic entanglement purification from ADS-CFT argument. And it is good to develop some numerical calculations of entanglement of purification because its properties still not so understood well. And also it is good to always think about some relation to other interpretations. There are interesting works, as I listed, which relates entanglement entanglement wedge cross-section to other quantity. Yeah, so I'd like to finish my talk, but before that, because I'm a last speaker, but still we have more workshops in AEI. It's going, but this is the final day of the workshop in Zeuthen. So I'd like to ask all of you to send a big hands to organizers. Michael and Carl. Thank you so much.
Okay, I think we should also thank Tadashi. And because it's the last talk, and I think we still have time to catch a few more trains, there is some time for questions. Johanna has one.
So you showed there's a matching between the gravity and the CFT calculation. And can you say again what enters on the CFT side out of the calculation? I mean, I'm always wondering, could we take an example for a CFT and then say discuss the Virasoro algebra or some operator representations? Where would this enter in this type of CFT calculations?
But so you mean the meaning of this calculation here? Yeah, so basically what we want to compute this SAA tilde. So we have this SAA tilde. Right? And A tilde is a purification. So we assume some low AB. We don't want to change low AB. It's the original quantum state, which is mixed state, and we purify anyway. And once we purify, then we decompose the system into AA tilde and BB tilde. So that it increases A.
So that's a spatial decomposition?
Yes, just decompose extra space into half. And once we decompose, then we want to minimize against all possible choice of this decomposition. This is something we do here. So here, let me go back. So here, this is the picture. So we originally start with the AB here. And this is an infinite line. This is standard 2D CFT which lives on the infinite line. And A tilde is just the other part. B tilde is the other part. This is the original purification. But this is too much. So this purification includes a lot of extra information. So this gives the entanglement entropy is very, very large. So we decompose the AB here. This is P. And the BB tilde chosen to be some middle point. We can call Q. This has a double logarithmic divergence. But actually, we can perform some optimization so that it changes the metric here. Then we can erase one of the logarithmic divergence. So that's the reason we get this just C/6 logarithmic divergence. Initially, we start C/3 logarithmic divergence. So we squeeze the metric and minimize entropy.
So just let me ask to clarify what's happening here. So are you trying to purify to pure states, but on different geometries than like a strip or like
actually
a plane?
We assume topology is the same actually. So this topology is the same, but this is actually we can just rewrite this way. This is just conformal map, and once we have this picture, we just change the metric. So we squeeze this region.
Okay.
So same shape of this. Same topology of the space-time, but we change the metric.
Okay, very good.
Sorry, about the same picture. On the left-hand side, is this the time slide, the part that you have A and B, and the ancilla part is the time slice of your original field theory, or something with an extended Hilbert space?
So originally, we don't need to use the same CFT, same Hilbert space. But here we are assuming everything is given by path integral of the same CFT. This is an extra input.
Yeah.
But among that, we change this actually metric. That means even changes the Hilbert space dimension. If you have imagined we put some UV cutoff, right? If we squeeze metric, the number of lattice points decreases. So even though Hilbert spectra looks similar, but we change the number of lattice sites.
Okay.
Yeah.
Is there any way to generalize this path optimization beyond CFT?
Beyond CFT. Actually, we wrote one paper which corresponds to some massive deformation of path integral. But computation is very complicated. We only work as a leading correction about mass perturbation.
So you do a mass perturbation there?
If once we put mass, then everything, computation becomes very, very complicated. So in CFT, we have a nice Liouville action, but perturbation is highly complicated. But perturbatively, it's possible.
So, well, I see one more person, but maybe let me ask a question myself. So I have a question about the field theory calculations on the lattice. So you were looking at intervals, like what you were depicting were intervals of like 4 lattice sides, and separated up to 1 lattice side.
Yes.
But like these are not really objects that have, in principle, like a nice continuum limit, right? Like these are like highly UV dependent. So what's the what are the limitations? Like what are like the biggest intervals and the biggest separations that you could?
That's really so. The reason why we look at the small subsystem is really numerical. Control. It's like it's numerically quite hard to go. Larger size of subsystem, and in that sense, anyway. So our result here, this result I presented, you cannot literally take a continuum limit, because it's like 4 side, maybe actually 4 side, and you can change the size of a spin chain infinite, but you can always keep 4 side. Otherwise, it's quite computation hard. So in that sense, it's a continuous limit is highly non-trivial, and it's still too early to say any definite result.
So were 4 sides, like 4 and 4 sides, so 8 sides in total, like the maximal size that you consider?
Yeah, it's just numerical constraint. I think mainly Alex factors. It's really related to computer resources and so on.
Thank you. Can you pass it?
I still have a question on this picture. So the fact that you need to split A and B at P and A tilde and B tilde at Q,
yes.
Is it a technical reason or is there a fundamental reason? So can I think of just a single interval and is complementary and try to optimize the unitary on the complementary and the interval in such a way that I get the minimal purification?
So anyway, we want to purify. So this is the original path integral. This is already purified. But the basic, simple way to purify is just to use the same topology and just call this region the purified space.
See, exactly. Yes.
And maybe you have even more non-trivial topology for purification. So that case, we can also add some extra path integral and purify it, but that's quite complicated. But so it's not so clear. That gives a smaller result. It looks like we increase entropy.
No, I was wondering what is the role of P and Q. So if you raise P and Q,
P is the original separation between A and B. So we have to prepare A, B, and somehow we merge this together. But if you don't like, you can just separate them as a 2 streets. But we have to fix these 2 points. Right? This length is the input, and Q is arbitrary. Q is just a parameterization of the choice of separation, B tilde. This is a kind of artificial parameter. So that's the reason we minimize. Sorry, we just use this. So we minimize against this change of Q here. Q is a parameter. We have to minimize.
Well, I think we can postpone it till prior discussion. So let us close the conference. I just want to remark that later today, all the talks are supposed to be online, in the sense that all the transparencies are going to be online. And also, like, the talks were recorded, and we're going to upload them to a YouTube channel, and everybody is going to get a link, or maybe we're going to put a link on the website. Okay? Super. So let's thank Tadashi, and let's thank all the speakers.